Hello and welcome to my final presentation for quantitative chemical analysis about EDTA titrations and my final assignment for Bronx science as a whole. Let's begin trying to do this 23 slide presentation in 10 minutes. So review questions. These are questions that we're going to answer today. Considering the titration of 50 milliliters of 0.01 molar silver nitrate with EDTA at pH of 9 at these different volumes. And then the reverse where we switch the analyte and the titrant, where we switch 0.16 molars, 1.6 molar lead ion solution added to 50 milliliters of 0.032 molar EDTA. I want to get to a power of lead of 3.62 at a pH of 6 consider at these different points, and we can interpolate to find that particular number. All right, work time, so go ahead and take a second to do your work. All right, welcome back. Let's get crack-a-lackin' with some terms, formulas, units, and constants. So here's some terms relating to EDTA titrations. Click here if you are, pause here if you're not familiar with all of these. And yeah, so this is what we're gonna, these are the terms I'm gonna be using, titrant and analyte, the most often one. Formation constant, familiar with most equilibrium expressions, it's just like that. Conditional formation constant is what we're gonna use because the fact that only non-protonated EDTA effectively binds to metals, and thus we care about the fraction that are not protonated. So we're going to multiply the fraction of non-protonated by the equilibrium constant. If you look at the equilibrium expression for EDTA binding with a metal, you'll be able to derive this fact for yourself. EDTA is the chelating ligand ethylene diamine tetraacetic acid. And finally, we'll be using the word region to indicate, to refer to different amounts of volume relative to the equivalence volume, because it indicates what kind of chemistry is occurring in this situation and what formulas we're using. And here, let's take a look at that. If you'll see, region 1 has excess metal, where there's very little EDTA added. Region 2 is your equivalence point, which you can refer back to. And the equivalence point occurs at the equivalence volume, which we're also going to be talking about. PM refers to the negative log of your concentration of metal. And finally, in region 3 is where we're going to have excess EDTA, where a lot of EDTA has been added. Let's talk about formulas and where they come from and their derivations. In region 0 and 1, the concentration of metal ions is simply going to be reduced by the addition of EDTA, and then you also consider the fact that it's being diluted. So that generates the formula: the final concentration of a metal with charge N is going to be equal to, proportional to the initial, but multiplied by some percent completion, which is the VE minus V over VE, and it's diluted by some VI over VI plus V. Dilution equation comes from the fact that, from the definition of molarity and concentration, and to find the final concentration, you multiply the initial times the initial volume and then divide by the final volume, which sort of makes sense physically. Region 2, we theoretically have all the available metal is bound, so the metal that is produced is from the unbinding of the EDTA from the metal. So we're going to be looking at the equilibrium expression for the formation constant, in this case the modified formation constant K prime F, which may be the concentration of bound EDTA over concentration of free metal and free EDTA. Excuse me. And since all of it is bound, theoretically any free EDTA comes from an unbinding situation, which is where you're going to get that minus X. And then every free metal ion comes with the corresponding free EDTA, where that's where you're going to multiply the X's at the bottom to get X squared on the bottom. And note that you're going to have to consider a dilution for the F prime, where the formal concentration is going to be diluted somewhat. Finally, for region 3 is going to be just like that. However, we're going to make the approximation that the amount with excess EDTA, we're going to make the approximation that any unbinding of free metal, unbinding of EDTA, note that this should say free metal, not free meal on the first bullet point. We're going to make the approximation that any free metal does not generally contribute to the amount of bound EDTA, and it's not going to contribute very much to the amount of free EDTA. And free EDTA is just going to be the excess EDTA. So we're going to go from K prime F is equal to F prime minus X over X times E plus X to K prime F is equal to F prime over X times E. Some units that are going to be important, some constants, are the fraction of free EDTA constant, which I'll show on the next slide, and the actual Kf itself, which is going to affect the equilibrium based on the identity of the metal. So here are two tables that track that. The Kfs are determined experimentally. Note that this table has log of Kf, and the alphas are also determined experimentally for different pHs, because obviously the amount of deprotonated depends on the amount of hydrogen that's available to interact. All right. Let's get into some solutions. Just a little joke there. So for question 1, let's start with part A, which is going to be You find the alpha at your given pH. In this case, it's going to be 1.8 times 10 to the minus 5. You'll note that I have terrible handwriting on my computer, so you'll have to follow what I'm saying with my voice, which is going quite quick. Part B is finding what your Kf for your given metal is. In this case, it's going to be, in the first problem at a pH of 9, the alpha is going to be 0.041. I was getting ahead of myself. And the Kf is going to be 10 to the 7.20. This is going to lead into your step C, which is your K prime F. In this case, is going to be equal to 6.498 times 10 to the 5 times 10 to the 5th. Our step D is finding the equivalence volume, VE, using the definition of molarity, which is going to be equal to 100 milliliters in this case. Step E is dividing each of your things, 0, 50, 90, and 95, into different regions. This is region 1. Then you've got region 2 at 100 milliliters, and region 3 is going to correspond to 105 and 150 milliliters, respectively. Next, we're actually going to start calculating for, let's go ahead, for region 1. We're going to be using the equation that we've just derived, where the final concentration of silver is going to be proportional to the initial times some percent completion factor and some dilution factor. So for 0, we're going to get that the PAG is going to be equal to the negative log of the initial concentration, because no EDTA has been added, which is going to be the negative log of 0.01, which is going to give us 2. From there, we're going to have to go to 50 milliliters, where we're going to get that the PAG is, by plugging into that equation, we're going to get that the PAG is going to be 2.602. By plugging in 50 for our added volume, for our initial, our equivalence volume 100, and our initial volume of 50 milliliters based on the problem. From here, we're going to go on to exact same procedure for 90, where the PAG is going to be equal to 3.447. Finally, for the last one, for 95 milliliters, we're going to get a PAG of 3.763. If you wanted to go even closer, for instance, 99.9, you might notice an odd fact that your PAG is going to be much higher than you would get for region 2 once we do that. And that is because it is no longer appropriate, very close to the equivalence volume, to consider the unbinding producing free metal to be negligible. In fact, there's such small quantities at region 2 that it is quite a factor of free metal from the unbinding of EDTA. All right, let's actually do region 2. Region 2, we're going to use the formula that we've just derived, which is that K prime F is equal to F prime minus X over X squared. In this case, F prime is going to be 0.01 times 50 over 100, which is going to be 0.003 bar. We can solve this for X by looking at this expression and realizing that we can subtract by K prime F on both sides. If we do that, we want to find when 0 is equal to F prime minus X over X squared minus K prime F. If we plug that into a calculator of some variety, and we set this equal to Y, and we want to find when Y equals 0, we get that the X value is equal to 0.0025. I'm sorry, that is the wrong number. We're going to get that the PAG is going to be equal to, consulting my notes, 0.000071, 7.1 times 10 to the minus 5th, which is going to give us a PAG predictively around there, which is going to be 4.1496. Note that I'm giving more more units than needed. You can refer to the presentation on propagating error as to where you should properly truncate this. Finally, for region 3, we're going to be looking at K prime F is equal to F prime over X times E. F prime, pretty easy to find. Just going to do a dilution, 0.01 times 50 over your initial volume plus your added volume. So, yeah, that works pretty well. And then finally for E, for E, you're going to be just considering how much EDTA is in excess beyond the equivalence volume. So you're going to be subtracting off all of the EDTA that should be bound by metal in that process. Doing this, remember to divide by 1 over to get your X once you multiply across. You're going to get a PAG for 105 to be 4.5122. And for 150 milliliters, excuse my cat, you're going to get a PAG of 5.5117. That's all we've got for this problem, but we've got another problem to do, and hopefully I'm not going to go too far over the time limit. I have before. If you'd like to check that out, please look at my longer version of this video. Now let's consider the second titration. Steps A through E are exactly the same, except you're going to use different constants for steps A, B, and C. Your equivalence volume is going to be 10 milliliters, and let's get into it. So for region 1, I'm actually going to call this region 1 prime because it's actually the same thing as region 3. You have to consider the fact that K prime F is equal to F prime over XE. An interesting thing to note is F prime is going to be calculated just how you think it's going to be, just a simple dilution. However, the interesting one is the E value. For E, you calculate E is going to be equal to your initial volume times your concentration of EDTA in this case, minus your volume added times your concentration of lead in this case, and then you take all this and you divide by your initial volume plus how much volume you've added. Where you can get this from is you have to note that there are different concentrations from EDTA and lead, so you have to figure out the moles of EDTA that are still available once you add in your little bit of lead. And that's where you get this from, and make sure to use this formula. Other ones will get you quite close to the right answer, but they will not quite be right in an actual chemical sense. From this, we're going to get PBs, of 15.2509, which makes sense. In this case, we're doing a reverse titration curve. Our next one is going to be 13.023. From here, you're going to get a 11.2596. This is for the next step up, which is going to be 9.9. This is the 9.9 milliliters. From here, we're going to move on to our region 2 prime, which is actually the same thing as region 2, equivalence volumes. You're going to use the exact same calculations anyways. Your K prime F is going to be equal to F prime minus X over X squared. Doing this, we're going to get an X value of, just consulting my notes here, of 3.849 times 10 to the minus 8, and you're going to get a PPB equal to 7.4147. Note that the reason this is not the same as before is because just like in the same way that all acid-base titrations or acid-base equilibria are determined by the KW, in this case, everything involving EDTA is going to involve this formation constant, which in this case is 10 to the 18.0. Plugging that in, this is what PB you're going to get. Finally, for your region 3 prime, which is basically the same thing as your region 1 in a theoretical sense, you think you use the same equation, and you sort of do. In this case, we're going to note that the concentration of PP, your free lead ions, at the end is going to be proportional to your initial by V minus VE times your initial concentration, which makes sense because past the initial is all you care about, and past the equivalence is all you care about, and up to the equivalent is just everything that that you've added. This is all the excess lead, and then you have to dilute it. So you have to consider what's available and then what you've diluted. And with that, you get some PPBs of 3.57475 and one of 2.1181. And these are for 10.1 and 13 respectively. With that, we actually want to figure out our answer, which was when is at 3.62, and you're not going to be surprised that's very close to 10.1. You can do a little bit of interpolation by 7.41 minus 3.57. These are PPB units across 0.1 milliliters. It's going to give you 38.4 PPB units per milliliter. Do a little dimensional analysis when you want your change. 3.62 minus 3.57 is equal to 0.045 PB units, PPB units, times 1 milliliter over 38.4, just a little dimensional analysis as I mentioned. And this is going to indicate that you need to decrease your volume of EDTA added until you get down to 10.099 milliliters. And that's our answer for that. Coming back to the slideshow, what do we have to do after this? Well, let's reflect. I think this has been a great presentation. I really love this class. I think that distance learning has been a little difficult to keep track of things, got to be honest. Don't have any kind of schedule whatsoever, and I'm doing a lot of work where I am right now, so it's very hard to stay on track of things. Despite that, I still feel like I learned a ton. I love the worksheets that we've been doing in this class, and this class has done really, really well at keeping me learning about things and learning chemistry, unlike some other classes. And with that, shout out to Mr. Mulek. And with that, I think that is, I'll gotta say, love Bronx Science, and I hope you enjoy this presentation. There's a little bibliography about where I've just gotten all of my sources from. All right, thanks. Bye.